So it's a distinct pleasure for me to present Professor David Hertzog, who today will talk about the first results and afterthought from the Fermilab Muon g-2 experiment. Professor Hertzog did his undergraduate studies at Wittenberg University, the one in Ohio, not the one in Germany, and obtained his PhD from the College of William and Mary. After a stint at Carnegie Mellon as a postdoc, he was for many years at the University of Illinois, and where he became full professor. And then in 2010, he moved to the University of Washington, where he's the Arthur B. McDonald Distinguished Professor of Physics. He received many prizes, among them a Guggenheim Fellowship in 2004. And for several years, he has led the Muon g-2 group at Fermilab. He was the founder and co-spokesperson for the group until 2018. And indeed, today he will talk about this. That is one of the highlights of the scientific discovery, scientific progress and scientific results in the last few years. So thank you very much.
Well, so thank you very much for the invitation. It would have been great to fly across the country and be in New York City and from Seattle to join you. But these Zoom days are hopefully soon over, not so long. So I'm sorry, it's still a remote talk, and I hope that'll be okay. And please, if you have questions or anything, don't hesitate to act as if I was in front of you and let me know. So I'm going to tell you the story. This is a wonderful picture. Shortly after the storage ring in 2013 made this long journey, which I'll show you some photos about, from Brookhaven, where it was built and used for the first experiment, all the way around, and arrived at Fermilab, and it was a very nice party. And then later that night, this ominous clouds came along, which gave us a little bit of a pause. So we'll see what happened after that. I'm going to try to be as inclusive as possible at the beginning of this talk. I don't care what field of physics you work in. I assume that you're not in the field of particle physics or nuclear physics for now. And then as I get deeper into the talk, I will try to show you a few of the things which should make you kind of think about how we go about our work and how you might trust the results. So there I probably will show you a few more technical things. So I would start off by thinking, you've seen these kinds of introductions before in particle physics talks where people are looking for new physics, but we all know that the standard model of particle physics represents a marvelous achievement. We know all the particles, we know the forces, we know the so-called rules of engagement for those forces. And so in some sense, what's not to love? It's an incredible achievement. But in the same time that somebody tells you all of that, you then hear some people say, yeah, but the standard model is incomplete, and all of the complaints begin to emerge. And this has been going on for a long time. It seems like it's taking forever to figure out how to do whatever is called completing it. So our theory friends are kind of doing two things typically. They're developing creative, what they call new physics models that fix something. So they fix dark matter, or they worry about the hierarchy problem, or there's the inclusion of gravity into the theory. Or one of the most things that intrigues me is the matter-antimatter asymmetry. Why are we even here after the Big Bang would have produced a symmetric amount of matter and antimatter? But then there's also theorists who are just proposing new aspects that we haven't thought about, like dark photons or time-changing fundamental constants or extra dimensions, things that may or may not be able to be experimentally accessible. And the experimentalist community on the other side of this are a little bit like the detectives in a crime scene, and we're looking for the smoking gun evidence that either supports or rules out the above. And negative results, they don't get a lot of publicity, but they can be very, very important. And because they rule out wrong models. But positive results are fun, and they might indicate something new. And the nice thing about today is today I'm going to tell you a positive story and not a limit story, a negative story. So how do experimentalists go about this? Okay, what do they do in this field of trying to go beyond? And typically, and I know you have a big LHC group there, so I think they'll appreciate that they've been successful with this tool. But usually, the best instrument is to smash particles violently together so that you can momentarily create high mass scales that are beyond what we have in conventional matter. And the other thing is they build their instruments at the LHC and any other pre-LHC colliders to be very general so that they can collect things in all kinds of different combinations and look at those interactions and recreate stuff. And the reason for this is it works. There's a lot of evidence that this has worked to discover the particles that we know. And of course, the most recent thing was this marvelous discovery of the Higgs. And here's one of the events, typically that is a Higgs event. Now, the thing about the Higgs, of course, it got a lot of publicity and so on, but arguably the Higgs is part of the standard model. It completes the standard model. And so you might say, well, what tools do we use to look beyond the standard model? So generally, there are two approaches. And the LHC did, in fact, go with this conventional idea of smashing things together. And I'll apologize, but I like this particular metaphor. This is a famous fort in the Indian Ocean that was never in its history breached. And I view this as sort of like the standard model, and it's a fortress of the standard model in which people are constantly attacking it. So we built this LHC, and we round one and round two of the LHC, and we've really got nothing in that apart from the expected. So the new thing in the LHC is the high luminosity version. So that's something like this. We're just bang, 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 firing cannonballs at this fort over and over and over. And we don't know yet, they'll start, whether that will eventually lead to a crack in the standard model. But there's another approach to this, which I like, and that is what I call the indirect quantum tunneling approach. So you can also go into this fort by digging underneath the thing and getting inside. And if you use that metaphor of bashing it down or coming through the quantum loop level, then you have a better idea of the physics community that I'm part of. And these pictures here are images of just but a tiny fraction of worldwide experiments that do follow that sort of approach. And I'll sort of mention to you a catalog of those kinds of ideas. So the question of whether lepton number is conserved, whether a muon can turn into an electron, or that's what these things are essentially saying. How do we, and coming back to that matter-antimatter asymmetry comment, we can look at electric dipole moments of neutrons and atoms and molecules, or we're huge efforts worldwide to look whether a neutrino is its own antiparticle. These are neutrinoless double beta decay experiments that are out there. Direct questions of whether we see dark matter through either weakly interacting massive particle searches deep underground, or in the inverse of that, in terms of the mass range, the axion searches. And here in our laboratory, in fact, this picture right here is just down the hallway from me, is the ADMX experiment, where the axion is also sensitive enough to be the dark matter. And they're sensitive at that level. And then there are questions of just deviations from standard model predictions. There's muon g-2, which I'll talk about. There's lepton flavor universality violation experiments. Nice, interesting signals at the LHC at Bell, and a new experiment that I'm co-helping lead, which is called Pioneer. We're also doing this soon. And these things, and again and again, and there's so many atomic physics experiments I could hardly rattle them off to you. So they go big, they go small. Here's a little one in our basement, and a big one, and some other large ones, but they basically all work. They're all custom designed to look for typically only one thing, though. They're not general purpose experiments. So for about 20 years, there's been one measurement that sort of stood out as being inconsistent with the standard model. And this This plot is a plot of time. This is a decade here or two. And the experiment at Brookhaven had this one result. There's not more than that one result, and it's placed here, and I'll come back to what this is. And the theory has been, the standard model theory has been moving along in that time period, resulting in 2020 with the update that now, compared to this experiment, has more than 3 standard deviation gaps. So it wasn't that way at the beginning, but something when we published here, it was about 2 sigma, now it's 3.5. So what do? Do you blame this experiment? Is this experiment wrong? Could be, easily. It's a hard experiment, or is the theory wrong? And this is similarly worth challenging. So what was that quantity? So let's step back on that quantity a moment. And there's an expression here. This is the anomalous, stands for the anomalous magnetic moment of the muon, this little a. And you'll see it's equal to g-2/2, the gyromagnetic ratio. So let's go to that. So here's an expression for the magnetic moment of a particle. It's proportional to its spin with some factors of charge and mass, and there's a g factor out front. This is called the gyromagnetic ratio factor. And if you have a spin 1/2 particle, point-like spin 1/2 particle, the RAC would say that number is exactly 2. So this is a 2. And we know that that's not quite a 2 for all spin 1/2 particles, because all you have to do is look at a proton or a neutron. A neutron has a big, actually, magnetic moment, and it has a charge of 0, so that doesn't work at all. And a proton is a very large magnetic moment. That's called an anomalous magnetic moment, the part that's different from 2 that makes it not 2 for a spin 1/2 particle. So that can talk to you about internal structure, but also you can look at virtual loops, back to this idea of this quantum loop thing that I mentioned when I was talking about tunneling into the castle. So the effects of virtual loops that encapsulate all possible interactions with this particle, all these diagrams, also leads to an anomalous magnetic moment. So what we call the g-2 test, the test for new physics, would be to compare the measurement of a magnetic moment like that to its prediction. So the question then comes next, well, how good is the prediction? So if I look at the way the prediction works for the G factor for the muon, we can start off some decades ago now. So roll the clock back into the late 40s, 50s or so, and you see the first couple of terms, which are the difference of G from 2 out here in the 3rd decimal place. And that's this diagram here, which was sort of the start of quantum electrodynamics. It accounts for almost all of the anomaly. And this term here is called the Schwinger term. And so anybody who's taken a graduate course in quantum field theory would probably had this exercise passed through their notebooks as they've done it or learned how it was done. And you'll see this diagram a few times. This is a muon line. This is in a magnetic field, and this is a virtual photon. So this is the lowest diagram. And this is famous because the answer to this diagram is simply alpha over 2 pi. It's an easy solution, and it's clean. And this is on the gravestone of Schwinger himself in Boston, that alpha over 2 pi. Over the decades, you can imagine drawing more and more virtual loops to this quantum electromagnetic diagram until you get here up to what's 5th order. These very complicated diagrams, there are a number of patterns such that there are 12,532, I believe, diagrams here in this order. And these have all been calculated all the way through. So what we know about QED is absolute, complete, and way beyond scrutiny from our experiment or almost any other. Along the way, though, this little diagram would normally, one of the diagrams you'd see along the way would be called vacuum polarization, where a virtual photon would have an E+ and E- here and reconnect. But you could make the diagram also out of a pi+ and a pi- or anything else with the right quantum numbers to connect to this photon. It turns out that that's a fairly large effect, at least on the scale of things. It starts to show up in these digits here. And this is the part that's a little bit tricky. The controversial part is to get this right. But where that comes from isn't a model of some theory at all. It comes from actually a very straightforward application of a few mathematical rules that basically involve just summing up data. And the data comes from E plus E minus goes to hadron cross sections. And this beautiful landscape plot shows you all of the inputs at this point of different channels, and they're done by dozens of experiments. And so to measure the total cross section here and weight it by a certain kinematic factor, which is well known, gives you this to the present level of precision that we quote. And that's what we quote. We quote this number from experiment. So it has mostly experimental uncertainties. Way back in, I believe, early 60s, people recognized that along the way, one would have to, well, as soon as the Z was really found, this made a lot of sense too. Anytime you have a virtual photon like this, you could substitute a Z in there. Of course, it's very heavy, so it's not going to happen with the level here. Or you could put a W into this diagram. And this is known incredibly well. It's tiny, but it's known very, very well, the electroweak effect. And the Brookhaven experiment that you saw earlier that I compared to basically was built to see this term. It was essentially not, at the time I joined that experiment early, it wasn't a search for supersymmetry or any words like that. We were really doing kind of basic physics of this sort. And we easily see this. If we don't have this effect, we'd be in trouble. And what's more interesting is you keep going out on the last digits here, you could ask yourself, what about other things? So what other possible new physics? Because anything that's new physics that couples to the muon is going to affect this number. So we're way out here in the digits to do it. So here, just to give a nod to my theory colleagues, some years ago, the theorists involved in this have got themselves together into a collaboration. So this g-2 hadronic theory initiative has met many times. This is a meeting in Seattle. That's me here. All the smart people are up in front of me or to the left or right of me in this photo. It's the way I look at it. And one of the breakthroughs that have been happening is sort of higher level diagrams. I won't mention them more, but things like hadronic light by light had been figured out how to do. They've done this on the lattice, and they've done this with data now. That was completely ambiguous way back in the day. And there's a catalog of this, an 160-page report that's published. And that's the uncertainty on the number right now is a conservative value of about 350 parts per billion. So that's good for everybody to remember. The scale of things I'm talking about will be in the hundreds of parts per billion. So in April of last year, we released the first result of our experiment, and we measured the G factor to be this number. There's a lot of you, but this piece, so if you look at it, what we really measure is this bit here, the way the experiment is. So we call ourselves g-2 experiment because we measured these digits. We assume the 2. And so this piece here is g-2, and the anomaly is then g-2 divided by 2, so it ends up being like this. I just wanted to walk that through to give people who aren't involved in this a little bit of a feeling where the origin of the name is. And so our final uncertainty combined with the previous result is about the same as theory right now. It's 350 parts per billion. So you can imagine we're completely balanced for the first time. And then one of the fun things we did that I helped organize this and push was rather than just put a short paper on the archive, we spent a little time writing everything down before we released it. And we worked with the editors of the Physical Review so that all of these papers were being reviewed, many of them blind to the number. And so we actually published all 4 of these on the same day as the release. And it's been pretty well received. But what we thought is we didn't know what we were going to get because we were still kind of blind. But we wanted to have all of the details written down so that if people wanted to challenge the experiment, they could read about it. So let me tell you now, with that introduction, the story behind this experiment, and going to slide into the experimental details, if that's acceptable with everyone. Here's a picture on our campus of one of our many meetings. And it's interesting to do this experiment with a group of specialists, if you will, from all of these different disciplines. We have particle, nuclear, atomic, optical, accelerator, and theorists in our collaboration, and everybody runs shifts. So we don't always even have the same language, but we're all just assembling this gadget to measure one number. And that's this number that we aim to get eventually to 140 part per billion, which requires 20 times the data that we had achieved when we did the experiment at Brookhaven. So the goal is 20 times the data, and that becomes kind of a metric for where we are. So the fundamental experiment is incredibly simple, and it has to be simple or it wouldn't work at all. You basically bring into this is a big magnet, and the magnet just has a vertical field. So like every undergraduate knows, a charged particle goes around in a circle in a magnetic field, a uniform field in a circle proportional to its momentum. So that is represented here by the black arrow. So this is just the direction of the momentum vector as it goes around and around. And the red arrow is representing the spin of the muon. The muon is a spin particle, and it's polarized. We're going to bring it in with a spin orientation. So what happens is, because g is not equal to 2, this red arrow goes around a little faster than the black one. So eventually, so it precesses. And the experiment is literally just the difference between the spin precession rate, the red arrow's rate of revolving, and the cyclotron frequency, which is the black arrow going around the thing, for the muons that are moving in this magnetic field. So this is the spin minus the cyclotron is what we call then the anomalous precession frequency. And that just has a simple expression. So all you have to do to first order, higher order, harder, to first order, you measure this spin precession frequency, you measure this magnetic field, and then you do long division to get the answer. And that's kind of what we do, is long division. Now, if you go deeper into the chapters of Jackson, of course, you immediately realize once you get beyond the freshman level going around a magnet that anything spiraling up or down would leave the magnet instantly if it had a vertical component to it. So you need something to keep the particles inside the magnetic field. So the idea there is you put in electric fields. So how do you put electric fields in? You put in electric quadrupoles. I'll show you those pictures, but that introduces something interesting. First of all, there's going to be a motion like this up and down, and you hope that that's zero at some level, a small correction. And then if there's an electric field there, you have the problem that there's a B cross E motional magnetic field created. An emotional magnetic field is suddenly a magnetic field, and then that would change the whole equation of trying to have measured the magnetic field in the first place. But what they discovered in the 70s at CERN was, if you run the experiment, here's the math of this. This is the anomaly. This is gamma. Here is just the relativistic gamma. So if you happen to run the experiment at a value of this gamma of 29.3, which is this momentum, then this term in parentheses goes to 0, and you have no effect from the electric field. So that's super important. And all of the experiments run at that, since this is the third generation that runs at that momentum to take advantage of this idea. So I like to list this, the way you can do an experiment to this many digits is pretty much miracles of nature. And here I'm going to rattle off 4 miracles that make this happen. I told you the ingredients for a moment. The first thing you need is a beam of polarized muons. And if anyone has done physics with polarized beams, they generally know that producing a polarized beam, an electron beam or a proton beam that's polarized, is a very big technical achievement. But Mother Nature gives you this for free. We just produce a pion beam, and a pion decays to a muon and a neutrino. And because of the left-handed nature of this neutrino, and this is a 0 spin object, automatically this muon comes out polarized. I see a hand up. Avish, did you want to ask a quick question?
Right. Hi. Thanks.
Hi.
I had a question about the previous slide.
Yeah.
Where you said this. So what we are trying to measure finally is A of
Yeah.
mu.
Yeah.
So if you know at what gamma this
Yep.
term cancels out, don't you have an estimate of A mu from there?
You only this term here is diluted by hundreds and hundreds of times compared to this. So this particular gamma you only need to know to a certain level. I will come back to this and show you this effect later in the talk.
Right. Thanks.
That's one of the important corrections.
Thanks.
So back to the list, you get the polarized beam for free, and that's really quite polarized in this forward direction. The second thing is what I told you when I showed you the original diagram, is that the spin precession frequency is proportional to g-2, not to g. So this expression here is proportional to g-2. Notice that what you really want is the anomaly. So you're not trying to, that gives you about a factor of 850 easier than measuring g. You can measure g if you had the muon at rest, but by pushing it in motion, you're measuring g-2. And then at this so-called magic momentum, this electric field, which we just talked about in that comment, the electric holding field doesn't perturb the spin frequency. And finally, I didn't say this yet, but how do you possibly know what that spin precession frequency is? Now you exploit parity violation again, which is in the decay of the muon to the electron. There's a bias that the high energy electrons in this three-body decay are in the direction of the spin of this muon. And we'll exploit that to figure out a beacon of where the spin direction is on average. So we take this thing up a little bit of a notch. What we end up in the end of the day is our collaboration measures two numbers. We measure this denominator, this numerator number, which is the precession frequency, and this funny looking denominator, which is going to represent the magnetic field. I'll come back to it. And then we multiply by constants of nature, if you want, that are measured by other people, from muonium experiments, from the g-2 of the electron experiment, mass experiments of this, and so on. And these things are all known well enough that we convert this ratio into the right plane. So how do we get the muons? So this is a top-down picture of part of the Fermilab complex. And the way it works is kind of amazing. We start off with a beam of 8 GeV protons, a rather intense beam that comes out of the LINAC. It runs around this thing called the recycler reed, but it's too big and it's too intense. And so we divide it into 4 pieces. So these little yellow things each represent about 10 to the 12th protons. And each one comes around one by one and comes along. And for those of you who remember Fermilab from a long time ago when it was a collider, they hit a target here which used to produce antiprotons, but now it is striked with a different polarity and produces pi pluses right here. And they go about almost 300 meters until they get to this triangle. And they go, and so now we have a beam of mixed of pions and muons and some background, and we're going to send that beam around this loop 4 times. The pions all disappear, and what's left is a pure beam of muons that go into the storage ring about here. So this is about 2 miles. So from the time this starts to the time they're done, we've got a couple of miles worth of running, and the muons have a long enough lifetime they can make it. So as they come into the door, here's a picture of this big storage ring, this big magnet. They come through these magnets here. We have a lot of instrumentation we built, and it has to bore through the back of this magnet through a tunnel here. This is literally a tunnel in the back of the iron, and then through a superconducting magnet here, which makes a zero field corridor, kind of like you can imagine a trolley or something going into a tunnel. And then they pop out here into a magnetic field, but they're in the wrong place. They're wrong place, and they have to be kicked into the middle by a kicker. So there's an incredible achievement here in pulsed high voltage, which produces a pulse like this on and off. It produces a sharp magnetic field, which is hard to turn on a magnetic field and turn off quickly, as you know from any kind of eddy currents and things like that. But that little crazy kick pushes things onto a central orbit, which runs around. So in order to keep the particles in, I told you we're going to need some kind of vertical containment, and that's achieved by a set of electric quadrupoles. So this is something like a penning trap. If you know what a penning trap is, there's a vertical magnetic field, and then we have electric plates here with positive charge plates, top and bottom, negative here. Therefore, a charge positive particle as it goes up, gets pushed down, and so on. And they're located in about 40% of the ring in these yellow areas like that. But they have to be turned on. Here's a disease of the first run. So I let you in on a problem now. Before any time the muons come into the ring, we have to turn these fields on. You can't keep them on all the time. There's too much sparking would happen. It's pretty high voltage. So we turn them on, and they're supposed to come up to a voltage and stay stable all the way through our measuring period. But we had bad luck. 2 out of 32 important high voltage resistors in this network were wrong, were bad, and as they were at high voltage, they had different RC time constants. So they didn't charge up until well into the time we were measuring with the muons. And the bottom line of this is this was our biggest systematic problem. It cost us 1.5 years to work out. I have something on this at the end, but if you're curious, I'll show you more in the backup. It's a very tricky problem. Now let's take a pause and driver. If you were a muon, this is what you would see inside the ring. There's quadrupole plates, you're driving around, there's all kinds of stuff in here. There's detectors we just passed quickly, there's more plates coming around, more detectors, and so on. So as you go all the way around the ring inside, the muons are in a vacuum. And the interesting thing about this experiment, unlike most nuclear and particle physics experiments for a minute, is we never let the beam touch anything. We bring it in and we circulate it in a vacuum until it decays naturally, but we don't hit a target and it doesn't hit another beam. It's a very different style. We just look at what happens to it as it decays. And so if you actually make a movie, because we are able to do the tomography of what those muons are doing, they're actually sloshing back and forth in this. We've never seen this kind of a thing in the past, by the way, but we know it from the equations of motion. You can calculate this. But to really, this is an actual image that verifies all of those equations, because the muons have betatron oscillations, and they're basically moving back and forth and breathing and going up and down like that. And that will impart its characteristic signature all over our data. We'll see this kind of an effect. So let me just, to tell you what you're looking at, if you were, this is where the muons are stored. If this makes sense, if it doesn't, you can ask me. This is as you go around there, imagine there's a tube. Just think of it as a circular tube in which they're allowed to be inside this tube. It's this big, it's 9 centimeters in diameter, and it's all within a very uniform part of the magnetic field. So this is what the boundary looks like. And we keep them in that boundary because we have things that anything that hits the red thing would be immediately lost. It's a physical object. So that sort of explains how we get the muons in. And then, but how do we measure the decays, and what does that do? So as the muons go around, they're going to go into these electromagnetic calorimeters. This is just some fun. One of my students putting together something. In fact, this is one of those crystals that's in there. And you can, if you look closely, it's very damaged because somebody shipped it to me without any wrapping on it. So we have about 1,300 of these crystals, and they're located all the way around in calorimeters, but also located everywhere is nearly 400 NMR probes to measure the magnetic field. So let's back to this frequency. So if you are a muon and you're going around the ring here, at some point you'll decay over the next hundreds of microseconds. The decay will emit a positron. The positron will have a momentum that's lower than the muon because of the same argument I made earlier. It will have a smaller bending radius. It will curl to the inside and it will strike a detector. There are 24 of these all the way around. They look like that. They're Trinkoff detectors. They're made out of lead fluoride. It doesn't matter. They make an electromagnetic shower and then they give a pulse. And the pulse is digitized by a very high speed custom kind of oscilloscopes. We have 1,300 of these. And you see that we can measure the time. And this distance, this time here is only 10 nanoseconds. It's very, very fast pulse because we have high rates. So you can see this particular pulse, the integral of this is something about the energy deposited. And now you have to look at the kinematics of muon decay in a boosted momentum frame. So this axis here is the energy of an outgoing positron from minimum to maximum. The maximum would be about 3 GeV for a 3 GeV muon. And what you see oscillating back and forth is the number of those positrons you get as the spin vector and the momentum are lined up, like now, versus against. So you can see that what's happening is the number of the high energy positrons is maximum now, and then it's minimum when the spins are in the opposite direction. So that alone is going to modulate how often we get really big pulses like this one. So if we take big pulses, that means those that are above this green line, and we start data taking, within a matter of seconds, we start recording how often we get them, and you get this characteristic frequency wiggle. And this wiggle is exactly what this blue-red frequency difference is. That's all you really want. You want to do that and get that right. So to make the magnet, we of course looked around. The investment in the original magnet was absolutely stunning at Brookhaven. It could never be built again. So it had to start with reusing this thing, and it had to be transported around the country and up through rivers and around oceans. It arrived here, and we were all happy. And then it had to be put back together again, which took about a year. These were just the coils. The rest of the magnet came by 50 trucks or something like that. And so we had to build it, build the iron yokes, put in the superconducting coils, establish a brand new huge cryogenic plant, and basically then shim this thing to turn it into a magnet from some that was actually usable in experimental physics. So this is a fun thing. This is where we bring in like a completely different technology than what most nuclear and particle physics people use. But this is a side view of that magnet that you saw. It's a C shape open to the area where the muons can decay. And it has a lot of pieces. And the way we measure it is using a pulse proton NMR. So this is a free induction decay. You knock a proton over, it spins around, and it winds back up again. That's the free induction decay signal. So what we do to do this is imagine we build a little trolley with 25 NMR probes on it, and we walk this thing around very closely around the ring, and each one of them, I'm going to do that for you here, each one of them is measuring locally the magnetic field as this trolley goes around. Here's an image of the trolley going. This is very early. This is when we were beginning to coarse shim the magnet. And each one of them is giving you a measure of the field. And when you see it, when you see this kind of a thing, the field in this little volume of about a cubic millimeter is uniform. And when you see this thing, it's has a high gradient, because you can see there's lots of frequencies. So then we came up with this idea, which was a brilliant idea of some of the people in our collaboration, to after doing all of the adjustments that took a year, just up here and down here, you make the last bit of magnetism, you fix the ferromagnetic surface to get rid of all of these lumps here. So watch what happens. We put 8,000 tiny little strips of iron, absolutely like a puzzle, all the way around top and bottom. And then watch, the red line is what we get, and the blue line was Brookhaven. And so in the end of coming up with this pattern of 8,000 little strips, we made the field 3 times better than it ever had been in uniformity in the previous experiment, which is very important, because then it goes right into the systematic errors. Okay, so that's all the hardware, and that's how the experiment sort of functions in a nutshell. I'm going to give you a real quick tour of the analysis. Of course, I can't go into details because it was years and years of work by dozens and dozens of people. But the main thing in this business is we have one and only one number we can provide to the community. We have to follow this Italian proverb: to trust is good and not to trust is better. So we have multiple analysis teams on every single thing you're going to see. And there's a lot of calibration alignment. People don't get a lot of credit for that important work. And the entire thing is done blind. And I'll show you completely blind analysis to the end. So I wrote this out. It's in the PRL. This is what I'll call the master equation. It's not really an equation. So please, I hate equations in too many talks, but if you just look, it's nothing more than some numbers divided by some other numbers. It's just long division. So what I did is just break up the numerator and the denominator into its pieces that individuals did. And they're basically, there's a clock with a blinded frequency. There's all the stuff in the numerator essentially is, what is this frequency? That's basically, what is this actual physical frequency? There's a measured one, and then there's a one that goes into the physics expression. And the measured one has to be corrected by things like the first question that I got was, what about that electric field? And that is a correction that we make, and it's a large one. And then in the denominator, all of these things are related to what is the magnetic field that those muons actually experienced while they were swimming around. And so I'll come back to those things each. First, this is just fun for anybody who is not in this business. And how do you blind an experiment? Neil?
Yeah, can I just ask, so you have all these terms in this expression. And I know you're ultimately going to get us to some, final expression with the final error.
Yeah.
Can you, for somebody who's not an expert, can you give me a sense of like which, and you said the electric field correction, and so I might, bug you about all these things a bit more later, but which of these ones are the ones that really could be corrections at the level of the error that you ultimately find?
I have a nice chart, Neil, coming up for all of those.
Okay, I will be patient. I will be patient.
But please ask it again, because I'm glad you're listening at that level. That's good. Okay, so this is the fun one. This one has zero, Neil. This is zero uncertainty, but it's a fun one anyway. So what we have, this is only a subset of all of the clocks that we have, fancy clocks that are ticking and GPS discipline clocks. So all of those things that you see are frequencies, and frequencies need things like discipline clocks that run at 10 megahertz. And so what we have is two people not in the collaboration who go into this at the beginning of a run, and they adjust the clock to tick a little bit different by plus or minus 25 parts per million from a nominal number. And they write the darn numbers down here and seal it in envelopes, which get stored in a couple of places for security reasons. And they're the only ones, and they check it every week. So they come in quietly, and this is all locked in cabinets, so no one can get to this business. The only thing we can do is we have a little thing to make sure that they don't screw up too much, or the hardware doesn't screw up, which is to basically, we can check the difference of a couple of clocks and know that the difference is stable, but we have no idea what the clocks are. So then on those detectors, you saw 1,300 of these crystals and stuff. We have a whole huge laser hut where we're flashing every one of these calorimeter things with a unique picture, a unique pulse distributed from a few lasers. So they get hit at the same time with the same amount of light, and we can calibrate light levels and timing and so on. So you have to just trust us that there's a lot of work here. The Italian team built this from the Optical Institute in Pisa. They're not even nuclear physicists or anything, and it's an incredible thing. So here's a fun systematic. This I find entertainingly fun when you get a hold of it. People who do high rate experiments know this word pileup. It's basically when two things smash into your detector at the same time and it becomes somehow indistinguishable. So and here's a spectrum of energies that you expect. So this is basically the energies that you would get from just collecting everything in the absence of pileup. It would go, as my mouse goes down here, to 3 GeV. These are the electron energies that would hit the detector. But what you really see is this thing that goes over here, but goes out to twice that. So how does it get twice that? We're gonna have twice that if you had 2 high energy electrons hit your detector at the same time. And that's going to change from early to late in our observation time, because the rate is high at the beginning, because it's extremely low at the end as they decay away. But what can happen that's nasty, that's just that's a counting problem. You could imagine a counting problem that doesn't bother you too much. But they have a different spin if it's like this. A high energy electron here's a muon, let's say it's spinning right here in this direction, and you get a electron with high energy. It takes a long time for this to arc its way into a detector. But low energy electrons, 2 and 1s that look like this energy here, come from a lot closer to the detector. But that means the muon has gone from here to here, which means its spin has somehow turned just a little bit more. And now you have something of the right energy, but of the wrong spin. And that changes, and that gives you a phase shift. So you have to be very careful in the subtraction. It's a fun thing. Okay, so suppose you did all that right, you corrected it, and you built this histogram, and now let's say this is as clean as you can be, you did a good job, and you want to fit it. So if you look at this, the fitting thing you would do here, this is what I call professor's level fit, which means I can do this fit. You would basically see that the population goes down exponentially. This is a log scale. This is just wrapped around. If you're not used to this, this is wrapped and wrapped and wrapped. Otherwise, this histogram is going to go across 4 or 5 screens. And so it just has a exponential decay here with a time dilated muon lifetime of 64 microseconds, and it has this oscillation imprinted on it. So if you fit that, you get a bad fit. You get a bad fit with all of these residual peaks here. And that's because earlier I told you the beam is sloshing back and forth. And because of that, the detectors look sometimes closer and further, and you get a little modulation, which appears right here. So we know that, we knew that all along. We know how to fit that. So our our fitting function is 22 terms, not 5. It's complicated. It also encodes this little slow part here because occasionally muons get bumped out of the ring from various fields and things. We measure those directly, so we get a handle on all of that. And when we get a handle on all of that, it's a bit more complicated, but then this is a typical fit. You can see the chi-squared is perfect. And the residuals to the fit is just 0, has featureless residuals. And that is what you call a minimal condition you have to achieve to get the data. So that doesn't prove anything, it's just required. So let's go to the denominator briefly. The main part of the denominator, that was the main part of the numerator. The main part of the denominator is this collection of stuff, which is the calibrations and the fields. And let me tell you what, and that was the thing I called omega p prime tilde of t sub r earlier, okay? So here you have the prime here represents proton NMR, but calibrated in terms of the equivalent precession frequency of a single bare proton, which is shielded in a spherical sample of water. So you can get a water sample. And this 34 degrees goes way back to Nobel laureate Bill Phillips's thesis experiment, where this thing was calibrated in terms of field. It's a kind of a cool thing. So we use that in that style. The little tilde that we decorate this involves the idea that we put the muons, folded that in there. So what we do to get this number is we have a whole team which does the absolute field. We have to do the absolute magnetic field. We have lots of absolute probes that are done, weeks and weeks of work in the summers without the beam. Then we periodically go into the ring and we measure all the field multiples. I'll show you, and we monitor it. And so, and by the way, this is a typical expression of the absolute field. So you have to correct for the water, the temperature, the shape of the probe, and any materials in it. This is its own business, but we know this extraordinarily well. This is a cool thing. This harks back to Heidelberg built this shell and this so-called trolley system for Brookhaven. The guts of it have been completely replaced by our Argonne colleagues, but there are 17 NMR probes and a lot of stuff inside here. And this thing comes out of a garage, automatically drives around inside the vacuum in the storage ring, and then parks itself in the garage every 3 days. And what it's doing is going into the field where the muon beam is not there at that time. Of course, you have to turn the muon beam off, and it makes these little slices. These are multiple projections of the magnetic field anywhere around the ring. So now you can work those all the way out till you get the integrated field, because you've measured its texture all the way around. So you might say, well, that's only every 3 days. Well, what do you do in between? In between, we have 378 NMR probes located above and below, which are constantly measuring, and we can record so that at a given place, this is some station 6, so that's somewhere here, we can record what did this trolley see, and then 60 hours later, what did the trolley see, and then what happened in this in between. And this is a kind of a random walk problem, which is called a Brownian bridge problem, because you know the endpoint. And so we do the mathematics to know exactly how to tie these together from the beginning to the end. And in the end of doing all of that, we produce this beautiful map here. The contours of the map here are, this is like 1 part per million, 1 part per million. This is all uniform field in here. And this is where the beam is. And the sharp observer will say, why is the beam here and not here? Well, we'll get there, but back to the question I was asked first about the electric field. So if you're still with me on that one, Avish, this is the plates, positive, negative. And imagine the following thing in this expression. If you're a muon going into the page with that electric field, do a R cross, B cross E there, and you'll see a positive upgoing field. So the motional magnetic field would be sort of vertical there. Now, if you do it on the other side, you're going to go, hey, Dave, this goes the other way. But that's, if you're over here, you're at high momentum. If you're over here, you're at low momentum, and the sign flips here. Right here, it flips back and forth. So both of those features cause an effect, which we can measure. It's very straightforward, but it ends up being proportional to the width of this beam and how centered it is. So we've recentered the beam since the first year. So that almost eliminates entirely this term here. And it's just the width of the beam that goes back and forth. But this is a pretty large effect. Notice this is larger than our uncertainty. We had 350 part per million, let's say, uncertainty, and this is a 489 part per billion correction with an uncertainty here of 50. Why is it 50? That's another little thing coming up. This is what the beam looks like. This is just not an exactly accurate way to tell you, but imagine if you're pitching up and down, then the magnetic field isn't always vertical to you. And that's it's a tiny uncertainty on this, but it's a fairly big correction again, but we know this very, very well. And the two corrections here, just bear with me for this minute. Here's that expression I told you, which has a phase. So what does phase mean? Phase stands for the average direction of the spin of that batch of muons when they entered the ring. It doesn't matter what it is, and we can't know it, but that's what it means. It means that's the direction at time t equals 0. So what would happen if the phase was not, here's what you want, but what if this wasn't constant? What if this somehow depended on time, the average spin? So if you break that down and expand that so that you turn it into like a Taylor expansion, then this phi goes to phi naught plus phi prime t, so that you can recollect, and now you have omega a plus phi prime t plus a constant, and so that means that you could have a phase shift, and a phase shift is death to this experiment. So we had two situations we had to worry about, and I've kept the details in the backup for this, but one of them was if those muons that left the ring by any chance all had a different spin phase than those that stayed in the ring. And we did that detailed work with a data-driven thing to show that that was practically nothing. But before we did the work, it could have been 150 part per billion error. So we did all the work and it ended up being 0, essentially. We did that here. The next one cost us 1.5 years, and this so-called phase acceptance correlation was all the headache of the fact that those resistors I mentioned that were bad had this feature that because they didn't stay stable, the beam always was moved vertically down and squeezed on every single fill. Came in, squeezed, move, squeeze and move. And so we had to go deep into the understanding of whether that caused an effect, and it did. And it was a pretty big effect. It's gone now because we fixed the resistors instantly once we learned they were bad. But it was a huge effect that took 1.5 years to settle on some kind of a value and an uncertainty on it. Then on the magnetic field side, we discovered something that the Brookhaven people never knew was there, and they were lucky. But with some very clever hardware, we found out that every time you turn on these quadrupoles, you pulse them, they make some micro-mechanical oscillations, so small but effective. So if you have plates that are moving a little bit, like my hands here, they created this crazy magnetic field. The time scale of 100 milliseconds means, oh, this is where the muons are, where the gray things, either here, here, here. If you blow that up, there's a little bit of a residual magnetic field as these plates are oscillating. We had to develop all kinds of special hardware, spent lots of summers developing hardware to measure this. It's really small. We were just lucky that it keeps crossing 0. But we put a huge uncertainty on it because we had to back analyze this to, by the time we learned this was 2 years later, so we had to back analyze it. Now we know it very, very well, and it's pretty small. But again, it's just luck. And the final thing is eddy currents. Every time you hit a kicker, you make a big magnetic field, you'll create an eddy current in nearby metals. And the nearby metals of the vacuum chamber will continue to fire a little bit of a magnetic field. And so we have very fancy magnetometers that work on the so-called Faraday effect. The Faraday effect is a really cool thing. You can ask about it if you wish. And finally, at the end of the day, we got all these numbers, and each one of these numbers had its uncertainty. That's here, Neil. So basically, all of those numbers are here. The corrections are orange. Those are fixed numbers you're allowed that add to the whole thing. And all of this is in part per billion. So the statistical uncertainty is basically, the total uncertainty is out here, and these numbers contribute to the actual value. But the blue is the uncertainty budgets. So the uncertainty budgets, here's the statistics uncertainty in the first run. Here's the uncertainty in us getting that frequency right. Here's the uncertainty in measuring the field right. And these are the uncertainties related to those little corrections. So this one is huge because it was from the bad resistors that were replaced. This next one is complicated, and we're working on it now. And I won't mention it much, but it's not big, but it'll be down by a factor of 2 the next time we publish. And the third one is that field transient thing I said with the micromechanics, and this one's now going to be very, very small. And so our goal is basically to have all of these numbers down here, and we're actually going to do better. The systematic goal is 100, and we think we're going to do better than that, actually. So with all that together, what do you do? This all happened in the year and a half of Zooming. Not one of us has seen each other since the beginning of this real deep analysis. So we, of course, get together. We have to vote. We have all those procedures. And when they vote 100%, I open up an envelope. Chris Polly opened up an envelope. We checked that the envelopes are the same. They're the same. We typed them into some fancy spreadsheet, not really a spreadsheet, but a fancy program. And instantly, this is the first time we see the result. We see it one time, and we publish this result. So as you may have known, we ended up with this value here, which confirmed the Brookhaven number pretty well. The two of them together make a nice average. The two of them together compared to the standard model is about 4 standard deviations. And people got excited about this. There were hundreds and hundreds of press articles around the world. So these are kind of fun. There was a big splash. It's always nice to have something happen in physics, as long as 10 weeks later it doesn't disappear. And so I just want to remind everybody that that was just the very, very beginning. In fact, this is our data accumulation up until more or less today. And this number is just this little bit here. This number will come out hopefully this year for the rest of this, which would be another factor 2. And then we're doing this one, and we're running this one, and this will go up to about here by July. By the time we're done in July, we hope to have this batch will be the next thing again. And then we're going to flip the sign. So on our side, this was Brookhaven, this was us, this is the average, and this is sort of where the funnel you could imagine. This is the projected funnel of error bars. On the standard model side, we know that number from the 2020 review. They are absolutely trying to get something like this. I put the legend over here on purpose because I don't know where that's going to go. I don't know how good they're going to get, and I don't want to speak for that group. But their intention is to be something like this. So you might say, okay, what if that was right? What could it mean? And the answer to this is probably better to say, look, a lot of people have written a lot of things by now. This paper has 549 citations since April. So it's definitely got people's attention, but they don't say what it is. There are tons of answers to this. And I would say, if I was being fair, most of these are a bit contrived answers. They have to tune a little bit. They have to be corners of supersymmetry phase space, which are still allowed, or leptoquark models that are allowed, and so on. So Dr. Stockinger, who's in our collaboration, sort of sorts these out in a big thing between possible and no. Some things are ruled out a little bit. I'd say some things are still possible. At this point, we've gone completely agnostic in the collaboration. Our job is to deliver the number, which is hard enough on our end. Now, you could also say, and you've had a talk on this at NYU not so long ago, maybe the standard model just will shift. There was a new lattice result published about the same time. It's a singular result. It's this result right here. So here's, to put it in perspective, let's see. This is our Fermilab number in yellow in the way this is projected. This is where we're ultimately going to go, somewhere in gray. And this is the number that we compare to, this so-called white paper. So we're here comparing to here. That's what I've shown you. All the things up here represent things that aren't in this compilation necessarily. There are some other versions of standard calculations of this, which were not included. They would actually make it bigger. They'd make it 5 sigma. The various reasons they're not included. And then there's all these different lattice calculations employing different kinds of lattices and different techniques. And suddenly we had this BMW one, which was sub% level, which is kind of a cool thing to have. But then they're all working it out. So among all the lattice teams, they're trying to figure out, are they all seeing the same thing and not? And I don't want to speak more, but hopefully they will get that right. And the thing is, if they're right, then if this is wrong, then you're talking about dozens of experiments that are somehow coherently wrong from different places, which would be very, very difficult to understand. I want to do a shout out to my team at the University of Washington. There's students all along here, postdocs, faculty, research scientists. It's been an incredible journey of working with brilliant people. And some of them are off as faculty now in different places, but all along the way, it's been pretty good. And as an outlook, I just want to close here. Our error will go down by a lot. The standard model will improve further. The fun is just beginning. It was a fun start to to this thing. It got a lot of people excited. And I just say, keep your eye out for our next release. Here we are in Elba, Italy, as a collaboration a few years ago. Before we haven't been together almost since. So thank you very much.
Thank you very much for this entertaining and informative colloquium. So now, if there are questions, please ask. I will try to monitor the hands, and or you can just
I can
ask.
see it too, Abby. I think, is that right, or no? Who? Oh, there's hands and clapping. Oh, I see.
Neil.
Yeah,
I
there's a hand, there's a clap.
Yeah.
Yeah.
Okay, so I'm happy with the answers to the question I had before. So can I ask just some more practical questions? The first one is just from a timing point of view. So when's the next release that I should expect from you, and what am I supposed to expect to change in that release?
Okay, I go back to that chart, which was kind of useful. So run two was completed with some improvements in the magnetic field's temperature and stability, which I didn't talk about. But the building was under designed with HVAC. It was probably our fault because we overpowered the building by many factors, so that even in Chicago, the heat never came on for a year and a half through the winters. So that meant that this is an important comment, it's just not anecdotal. That meant that the building was going up and down in temperature, and that meant that the magnet was going open and closed like this, okay? And that meant that the magnetic field was just swimming up and down. So we were tracking that, and that is improved completely now. The building is perfectly flat. As of run 3, it's dead stable. The second thing was this kicker, this thing that I showed you was awkward to build. In the first 2 years, only could kick the beam kind of onto the orbit, but not in the middle of that circular thing. By the 3rd year, and just before, maybe a month before COVID hit, we finally got enough improvements in the kicker, all high voltage stuff that's complicated to talk about. We can now bounce it into the middle. All of those reduce systematic errors directly. The stupid thing was these bad resistors, which of course we fixed. They were, it's a side story, not worth saying why they even were there. But that kept the beam stable again. And also the losses of muons have gone from what it wasn't big anyway to almost negligible now because of moving the beam into the middle. So that all represents the conditions we're running in run 4 and run 5 are extraordinarily clean, what we're doing right now. So this batch of data, which you asked about, is all produced. In fact, I could show you fits to all of this. I could show my grad students fit all of this data, 100%. Good chi-squareds, all that kind of stuff. The magnetic field work is 2 months from now, 100% done for this. All the systematics are almost done in a couple of months. The problem is there's 7 groups analyzing this for these frequencies, and we have to let everyone work their different methods together. So the feeling is we're aiming to, we still say something like the end of this year sometime, and we got to go through all of these steps to make sure everything's consistent. But we can definitely see the light at the end of the tunnel. Meanwhile, we're starting the production of this stuff. So all the pre-checks are done, and the final heavy lifting checks the heavy lifting production is starting. But we're probably going to combine all that together. So I'm no different than you. I want this to go as fast as possible.
Well, I'm not so much saying that I want to go as fast as possible. I just,
I want it to be right.
My own mental, I just am curious to anticipate. Okay, then from a less timing point of view,
yeah.
I don't know what to call it, but the micro vibrations that the Brookhaven collaboration did not find that you did find.
Yeah.
From an anecdotal point of view, how did you find them that they did not find them? And does it make you concerned?
No, we analyzed theirs. There was enough of us from that experiment that we analyzed the effect that it would have had on them, and they were just lucky. The following reason, the way when you see this picture, and by the way, we've measured it everywhere with the peak probe trolley and everything. What you see here is the beam comes in at Fermilab in the sequence of 8 pulses, boom, 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 like that, okay? And this timing between those happened to be a resonance of this mechanical thing, this 10 millisecond difference. Brookhaven had a slower, injection of the beam, and it was up, so it countered, and so it never built up the same level. So they were kind of lucky that we analyzed the effect, and it was very, very subdominant in the Brookhaven conditions compared to ours. But it wasn't zero, but it was subdominant compared to anything they had. So they were okay. And for us, it's just a matter of mapping this every single place around the ring with this gadget. And it's very hard. So how did you find it? You can't, and first of all, NMR is milliseconds timing. This is something that's happening real short. So how the hell do you find something that's happening when your free induction decay is kind of milliseconds level? The idea was to start the free induction decay systematically, moving the start of that and getting the first derivative of the beginning of that. And so we had developed that technique. We developed it here because we were interested in completely something else, which was 60 Hertz. What if we wanted to lock it to the 60 Hertz to see if there's anything? So then we started locking it to the injection. We locked it to the injection, and then we saw this. So to make this kind of a plot, you have to sweep systematically a lot of measurements across and add them up until you get this coherent answer. Does that make any sense, what I said?
Yeah, no, that makes sense.
And there was a brilliant postdoc at Argonne National Lab who just took this and, off-scale guy that just made it, figured it all out, measures it, analyzes it. So that's pretty cool.
Thank you. Thank you, David. Other questions? Maybe I can ask a very simple one. Is yours the only experiment that measures a mu in the world now and for the foreseeable future?
Are you asking if we're the only one?
Yes. Is it, or is there anything either?
There is another experiment which for quite some time has been developing a different way to do this at J-Park, at Jefferson, at J-Park in Japan. And they've been limited in getting going for lots of reasons. But they're doing it in a very, very low energy, ultra uniform magnet by starting with a beam. I could explain it, but it'd take me a while. But because of the nature of doing it not at this particular momentum, and because they start with a source of polarized muons that come from muonium, which is 50% at most instead of nearly 100%, they can at most get to the level probably of the statistics of the Brookhaven experiment, but it would be very nice to have another version of this, even at that level. They won't, I don't think they could go to this level here, and they haven't really started that much. They've done a lot of technical things to develop the idea of this, but it would be great fun if they could do it. But that's it. Otherwise, there are people that have crazy ideas. There's for sure true, but going from an idea to being on the real Riemann sheet is another thing.
Thank you. I see Alan has a question.
Yeah, I don't have a question. I'm just going to make a comment, which is NYU was on the MECO experiment from 1997 to 2003. And we interacted a lot with the G-2 people. And it's just been a pleasure over the years to see how it's developed and to see you get to this point. I wonder what you must feel like, because it feels great for me just observing it.
This has been a really lucky thing to have jumped into in my career 30 years ago. You lay, as an experimentalist, as a theorist, it's different. As an experimentalist, you put your cards on the table and you hope Mother Nature's kind. At some point, you have to execute, and you get involved in these things for a long time. So it's pretty fun. But you must be pleased to know that mu to E is coming along pretty well.
Yeah, very much, very much.
Mm-hmm. Very good. That's nice.
Thank you, David. Are there any other questions? If not, let's thank David again for his talk. Now we know much more than before, some of us at least. And thank you again, and good luck. We are waiting for the next release.
Yeah, thanks for the invitation. And if you have any thoughtful follow-up questions that you want me to answer, just shoot me an email and I'll do my best.
Thank you.
Cheers now.
Thank you so much.
You bet.